Begin. Yep. So, yeah, welcome everybody, and especially welcome to Dr. Flinth. Dr. Flinth is an assistant professor at Umeå University, and he's also a former 1W-MINDS organizer for the European continent. So we are incredibly happy to have him here to tell us some of what he knows about whether or not neural networks learn symmetries and data, and I'm interested in seeing what you have to tell us. So I'll turn it over to you.
Thank you, much for the introduction. Also, thank you very much for the invitation and giving me the opportunity to speak in this seminar. So yes, the talk will be about neural networks and whether they learn symmetries directly from data. The talk will be based on 3 papers. These 3 papers I wrote together with Fredrik and Oscar. So they're both the colleagues of mine here in Umeå. Oscar is my PhD student, and Fredrik is an associate professor here in Umeå. So when we talk about symmetries in neural networks, we can mean a lot of things. What I mean is the following. We imagine that we have a group G that acts through linear actions on the input and the output space. And then the symmetry in the data comes from the fact that the learning target, the function I'm trying to learn, is equivariant towards these actions. So first applying the group action, and then the learning target should be the same as first applying the learning target and then the group action for any group element. So for any group element G, this diagram should commute. So one example would be the following learning task. So imagine that our input data are point clouds, and the task is to detect and find the apparent line in the point cloud. Then, of course, rotating my point cloud means that I should also rotate the line that I'm predicting. So this diagram commutes. I have equivariance. And here we sort of have the same representation on the input and the output space. One can also, and it is important to also look at cases where the representations are not the same. And a good example for this is invariant learning tasks. So this is an example of that. If I want to predict that this handwritten number is a 7, that prediction should, of course, not change if I translate the 7 a bit. And I can encode this in this framework by saying that my output representation should be the trivial representation. So the representation that for any group element does nothing, outputs the identity map. And here we also nicely see that whenever I say equivariant, we could just as well, so a special case of that is talking about an invariant learning task and an invariant function. Now, let's say that we have a learning task where we know that there is some symmetry like this in the background. The question would then be, how should we handle this? So broadly, we can say that there are 2 meta strategies for this. One is to use data augmentation. So I simply make sure that the training data I pour onto my network is symmetric, in the sense that it should be equally likely to see a data point X and a label Y as seeing the transformed example. And then we use our favorite model and try to learn this data, and we, so to speak, let the model learn the symmetry. The other strategy is to make something when we are designing our model. So we make sure that the model is symmetric by design. For all the parameters that we could choose, we should have this equivariance condition also for my, for instance, neural network. And importantly, this is true that independent of the learning. There are good reasons intuitively for doing both of these things. So if we have a symmetry in the learning task, it intuitively seems like a strong inductive bias. So we should try to use that somehow. And we should do that by incorporating into our model design. One could, however, also argue that when we are specializing our model, we are restricting it. And we're hindering it from kind of exploring all the possible functions that it could represent. So what we instead should do is to take this vast power we have in these machine learning models and just trust that they will handle the symmetry in a good way. And this debate somehow has become more intense during the last years. So early, when these equivariant models were introduced, they performed well in many applications, particularly relating to science. So particle physics, inverse problems in quantum chemistry, there we have all of these forces acting on things like acting like vectors that transform in certain ways under, for instance, rigid motions of the molecules or something. Then, so many things happened, but one thing that happens was that the third version of the AlphaFold model came out. So in early versions of the AlphaFold model, they use some kind of explicit encoding of certain aspects of the architecture of the protein folding. The third version opted not to do that. They use a transformer without any equivariance properties and simply train it with a lot of data augmentation. And this seemed to work. And this sparked a lot of interest, and there were more than a few publications that came out that supported this. So we should forget trying to build in the equivariance into the model and simply use data augmentation. So one paper one could highlight here is one called "Swallowing the Bitter Pill," and the message of this paper is really that we should swallow the bitter pill. Although this thing with equivariant is nice mathematically, it's not the best way to handle symmetries. We should use huge models and train it on augmented data instead. This then caused other groups to do other experiments, and there have also been publications pointing to these equivariant models to really be better. So in these papers, the authors argue that if you compare models that are equally large, so if we look at models with the same number of parameters, since the equivariant models also are smaller, they perform better in relation to their size. So in short, the equivariance models scale better. So both intuitively and empirically, we have strong arguments for either strategy. Now, what do we know? What do we know theoretically? There is, in my opinion, there's still much left to be found out here. And I think the real issue here is that when we augment our data, we are not doing something to the training architecture. We are doing something to the training itself. So in order to fully understand augmentation, we need to understand the training of neural networks. And this, as we all know, is quite challenging. And because of many reasons, but I think partly because of this, most studies up until now have been confined to simpler models. There is a wonderful line of work on something called feature averaging. I will explain later what that is, but the main idea is that we take a non-equivariant function and then apply a linear operation to it to make it equivariant. Kernel models have also been considered. These are also linear, and we also have the linear neural networks, so neural networks without non-linearities in them. And in all of these publications, there have been results shown that point to some kind of weak equivalence between augmenting the data and restricting the architecture to the equivariant. But the core of the issue is still there for bona fide neural networks. So it's still an open question whether a neural network trained on symmetric data will become equivariant. And in particular, and this will be the main thing I will talk about today. So if I train my neural network, on symmetric data, will I find the same structure that I would get out from equivariizing the architecture? Okay, so let's speak about that for a minute. What do we mean by equivariant neural networks, and how do we construct them? So let's fix some notation first. So a neural network, as we all know, is a chain of linear maps between certain intermediate spaces xi, and they are trainable. And in between them, we have some fixed non-linearities that act on the intermediate spaces. So my neural network, I can say, is parameterized by this tuple of linear maps AI. And let's abstract that into one object A, living in this direct sum of the space of all linear maps between the intermediate spaces. And we will refer to that space as as a calligraphic age during the entire talk. Now let me say that there are many ways one can make a neural network like this equivariant. Let me first mention two I will not speak about that much today, and then we will get to the one I will speak about. But one thing one could do is, in particular, if we want to train an invariant network, is to simply take our data, apply some pre-map phi, so calculate some invariant features under the group action, and then use an unconstrained architecture on those invariants. And one can actually prove that from a theoretical perspective, this is enough, in the sense that when I do this, I will obtain something which is universal. But still, there are other ways to do it, which seems closer to the idea of machine learning, not to have some handcrafted thing first and then unleash the neural network training, but really to have machine learning all the way through. Another thing that I mentioned before is this feature averaging operation. So what we do here is that we take our neural network and then we turn it equivariant by applying this integral operator to it. And I think it's easier to see what happens if I show this sketch. So what we do with each data point is that we calculate all transformed versions of the example, then send each of them through my architecture, and then in the end average. So if I'm only looking for a invariant thing, I would really take the average, but if I want to have something which is equivariant, I also need to take this weighted average with the output representation in the end. The main weakness of this is that it will become quite computationally intense, in particular if we have a large group. So also at inference, we need to send all transformed examples through our network. And if we have a large group or even infinite group, this will become heavy, either from a time perspective or from a memory perspective. So now that I've mentioned this, let me come to the main player today, the geometric learning approach, if you will, and that is to use layer-wise equivariation. What do I mean by that? So on the top row here, I have my neural network, the intermediate spaces and the linearities and the non-linearities. So what I do now is that I say, okay, in addition to my input representation and my output representation, I also prescribe some way that my group acts on each intermediate space. Then I say that, okay, I choose my sigma i's to be equivariant with respect to these representations, and I constrain my linear maps to also be equivariant. Then in this commutative diagram, I will by construction have each square commuting, and therefore also the entire thing. First going down and then all the left means first transform and then the neural network. And first left and then down means first neural network and then output representation, and this will then commute. So I could also say that I constrain my weight to be in a certain subspace of age, and this age is this age D space. So I make sure that every linear map in the network is equivariant. And I can write this as the ones that are fixed by this lifted representation. So I put this here because I will need it later in the representation, in the presentation. Sorry. So each map here we act on each linear map by this concatenation of the different representations. And this is the natural way to define it. It's really the map that does the same thing as first undoing the transformation, then applying the original map, and then rotating it back, so to say. This is a natural thing to do, and this is something that people also do. For instance, if we perform this construction on a fully connected neural network, if we choose the translation operation on each space, we naturally obtain convolutional neural networks. So the argument is that in order to make this square commutative diagram commute, we will need the linear map to commute with the translation, and that then enforces us to use a convolution operator for A. And here one could maybe point out that in this setting, it's not hard to make the linearities equivariant. If they act pixel-wise, they will of course commute with translating around the image. Yes. Another example which one can view as using this framework is actually the case of learning on invariant features. So what we do here is that we view this invariant feature map we precompose our neural network as the first nonlinearity. And then we prescribe our representations like this. On my first two spaces, I use the representation I had from before. And then on all other spaces, I have the trivial representation. Then if we read out what we mean by choosing the linear maps and nonlinearities equivariant, we get the following. So we get an equivariance condition for phi, but since we use the trivial representation on my feature space, we actually get a condition which says that my invariant feature map should be invariant. And also, since I'm using the trivial representation everywhere, my condition for the late layers to be equivariant actually turns into nothing. It turns into that the map A0 should be equal to A0. So I have a completely unconstrained architecture from that point on. Now, one should maybe comment here that in my sketch, at least, I've said that the first linear map here should be the identity. So this is a fixed map. This does not really play along with what I wrote down before, but it actually leads me to the next slide, because if we want to go a bit further, then only multilinear perceptrons without bias, so fully connected networks without bias, we need to work a little bit more. So up until now, all linearities have been completely unconstrained. The nice thing is that with a simple technical construction, we can actually include a lot more neural network architectures into a framework. And the trick is to say that I confine my weights into an affine subspace L. So let me go back. So here the affine subspace would be the first linear map should be the identity. Another example one could do is to include multilinear perceptrons with bias. And the idea here is this standard trick to show that all affine maps can be viewed as linear maps. I extend all my vectors in the framework with a 1, and then I confine my linear maps to be the ones of this form. Then what this linear map does on the extended vector is exactly the same as applying my affine map to the original one, if we look at the top row. Another thing one could get into the network are so-called recurrent neural networks. Here the idea is to use the same layer again and again in the network. And this is, of course, an affine constraint on my linear maps. I could also do residual networks. So in a residual network, we actually do not learn the transformation from one layer to another, but we rather learn a difference to the identity like this. And this we can put into the networks as into the framework as follows. So we introduce an auxiliary space here, the blue space, which is xi times itself. And then I first prescribe my linear maps in the first steps to copy my x, and then apply another linear map to the output. In the non-linearity, I would then apply sigma only to the second argument. And then for my second linearity, I prescribe it to be equal to the sum map. And then just to formally make this play with what I just wrote down, I say that the final non-linearity is an identity. This completely corresponds to my layer xi plus sigma I x if I constrain the linear maps to be, as I said. And all of these spaces that I write down here are either points or affine spaces, so it's fine. One could do more things here. One can, for instance, look at the convolutional neural networks also in this sense. And one can even do transformers. But let's not get bogged down in this. The important thing is that for most neural network architectures that we can think of, we can actually describe them by viewing them as subsets of multilinear perceptrons, and the subset is actually in form of the weights lying in an affine subspace. Okay, so let's summarize what we've done until now. A neural network is a chain of linear maps and non-linearities. If we choose these A's without constraint, we end up with an MLP without bias. And we can make these equivariant by choosing A in this subspace HG. And that corresponds to making this commutative diagram commute. Then if we want to describe something more involved, we confine our weights to lie in an affine subspace L. And we can make these equivariant by simply confining them further to also lie in my space HG. So for the equivariant architectures, I'm really only playing in the intersection between my subspace of admissible weights L and the equivariant ones HG. And I then end up in a subspace that I call E. So E are the weights that I use in my equivariant version of the architecture. Okay, if there are any questions, stop me now, because now we're going to go on to the next part. There does not seem to be any. I have confused you enough, so let's continue. So now let's try to analyze augmented training dynamics in this setting. And I can already now say that we're going to focus on the training dynamics close to this space set of equivariant weights E. So what do we mean by training here? Well, I assume that I have training data distributed in some sense on my space of data and labels. And then if I have a loss function, I can define a risk as follows. So I measure the loss between my output of the network and the label, and then I take the expected value over my distribution. Now what I want to do is that I want to train my weights by minimizing this risk. And I do so using gradient flow. And I can do this in two ways. So I can train it in the normal mode, so confining the A's only to the L space and then applying a gradient flow like this. Here, pi L is the orthogonal projection onto the tangent space of L. That makes sure that I stay in L. And if I train it in equivariant mode, I only minimize over E, and then I do the corresponding gradient flow there. This is not the way one would write it down, probably in code, but one can quickly realize that as long as I use parameterization maps, so things that really take weights and coefficients I store on my computer and embed them into these L's that are orthogonal, what I actually obtain when I perform the gradient flow for those coefficients are these equivariant flows that are projected onto TL and TE. Okay, so here I've not said anything about the data. This is where my augmentation takes place. But with these notations, it's actually not that hard to write down what I mean by augmentation now. So what I do is that I change my training data distribution. So instead of just drawing an X and a Y, I draw an X and a Y, and I also draw a group element according to some distribution. For almost in all of our theorems later, we will assume that this mu is the so-called Haar measure of the group. So somehow I assume that I draw this uniformly at random. This means that I will get another risk function. So I get now an expected value both over the draw of X and X and Y and the group element. And the corresponding gradient flow for the augmented case is that I simply minimize this function instead, the augmented risk, still using my gradient flow training procedure. Okay, now let's try to analyze these flows. And as I already say, we want to look at the dynamics on this space E and close to it. So right now, anything could happen. It could be that there are points that are critical on E for both the augmented and nominal flow. There may be points that we find with my nominal flow, so critical points for the nominal training dynamics that turn non-stationary when I turn on the augmentation. And there could also be points with the other way around. So things that are not stationary for my nominal architecture, but turn stationary when I turn on the augmentation. And this is really what I want. I want my weights to find these equivariant subspace, because then I know that my architecture will also be equivariant. And the same relations are, of course, also possible when we compare the augmented and the equivariant dynamics. Okay, so how should one go about performing this analysis? Well, the most important realization is actually the following. If we make this general assumption that all my nonlinearities are equivariant, we have the following relation. So let me decipher what this says. So it says that applying my neural network to a transformed example is basically the same as applying the same neural network architecture to the non-transformed example, but with transformed weights. So the augmentation sort of is related to an indirect action on the weight space. How does one go about proving this? Well, it's a lot of you need to write a lot, but it's not that hard. So the realization is that when we write down the definition of what it means to transform our AIs, we realize that the diagram here will commute. And then if we look at what that means, taking the route on the top and then down means exactly doing what's on the right side, and then first going down and then to the right, that corresponds to the left side. So we have an equality between those two maps. And now things get interesting. So transforming the data corresponds somehow indirectly to transforming my weights. However, this lifted representation, that is a map from age to age. It takes a map as a set of linear maps in the ambient weight space and give me something that is in the weight space. It's not necessarily so that if I take a admissible weight and apply my transformation to it, I get something in my admissible weights. So these affine subspace are somehow special, and we define them as being G equivariant. So sorry for the LaTeX error here. I call my architecture or my affine subspace G invariant if applying the lifted transformation to it keeps L, gives me something which is also an L for all my group elements. Let's look at some examples for when this is true. So a trivial example is when I have an MLP, which is unconstrained. Then this condition is empty, so then it's, of course, true, and it's true regardless of which group I have and which action I have. An equally trivial example is when all of the representations are trivial. It's then not hard to realize that this action on the weight space then also turns trivial. It does nothing to my weights. So when my representations are trivial, every architecture is invariant. A slightly more interesting example is the example of CNNs. So let's write the convolution operators with a filter. Let's denote that as C phi. Then we can show that if we look at the rotation action by 90 degrees in a pixelized image, then applying the rotation transformation to my convolutional operator exactly corresponds to rotating the filter. So that for one shows that if I look at the space L of all convolutional operators, I will stay there when I apply my rotation. In practice, of course, when we train CNNs, we actually confine these rotational filters to have support in certain sets. So having them in square is quite popular. And those squares are, of course, also preserved when I rotate them by 90 degrees. However, I could also confine them into a more exotic space like this. So if I confine them to the red set, the cross there, then I would obtain an L which is invariant, because if I rotate that cross, it will stay across. If I, however, use the asymmetric support on the right, then I will no longer have an invariant L, an invariant architecture. Remember this example because we will use it in an experiment later. Okay, so why is this important? It's important in our analysis in the following way. So let's assume some things. Let's assume that the loss function is invariant. So measuring the error between two labels does not depend on if I transform it, which makes sense, because if this is not true, there will be portions of the output space where the architecture will be forced to rather be. Let's also assume that all of the representations in both the input and output space and in the intermediate space are unitary operations. And as I said before, I augment using the Haar measure. So this is in some sense the uniform way of choosing a group element, in particular if I have a finite group that really corresponds to choosing one of the group elements uniform at random. Under these assumptions, I can use this equation I have here to actually lift the augmentation operation to a transformation of the risk function like this directly. So in that case, the augmentation function will be a symmetrized version of the nominal risk. And that in turn, and this is maybe a bit non-trivial, but it's not hard. If we then look at the gradient at a point in my equivariant subspace, it turns out that the augmented gradient is actually exactly the projected version of the nominal gradient. And once I have that, I can really start analyzing my set of critical points on E. So let's define some sets. Again, I'm only looking at the equivariant points, and then I look at the points that are stationary for my different flows. And then my question is, are these equal? And it turns out that yes, they are. If I assume that my architecture is G invariant, then the following happens. The equivariant space is invariant under the augmented dynamics. And furthermore, the critical points for the augmented and the equivariant dynamics are exactly equal. So on E, the architecture, the weights that I find with my augmented network are exactly the same as the ones that I would get if I perform this equivarization procedure. And what I can also say is when augmenting, I will make points equivariant on E, but I will not make, I will only make those equivariant that are missed by my nominal architecture. So if something is already stationary for the nominal architecture, it will not turn non-stationary, for my augmented network. And the proof sketch goes something like this. So on E, I know that my augmented gradient is equal to the projection of the nominal gradient. And then if I have this relation that applying the lifted transformation to my weights keep me in L, then I can actually argue that the concatenation of projecting to HG and to L exactly corresponds to projecting to E. And once I have this equation, everything follows. So if the first side is 0, the last side is 0, I also see that my augmented dynamics will always give me gradients which point in the E direction, so I will stay there. And if I have something which already is a stationary point under my nominal gradients, it will stay 0 after augmentation. Now, I've tried to be really careful here and only say things about stationarity. Yes, and well, the interpretation is what I said. So when I turn on my augmentation, I will turn points on my equivariant space stationary. However, those are exactly those that are also stationary under my equivariant flow, but were not stationary under my nominal flow. So if I look in my 6 alternatives here, these 3 are the only ones that are okay. There are no points that I hit with the nominal dynamics, which I then miss by the augmented dynamics, and vice versa for the equivariant and augmented dynamics. Now, this is, of course, only about stationarity. So I've only talked about when the gradient is equal to 0. One can also look at the stability of the points, and then we can say the following, that if we have a point which is strictly stable, so it's really a strict minimum of my nominal dynamics, it will stay a stable point for the augmented and the equivariant dynamics. And if I have something which is a strictly stable point under my augmented dynamics, then it will also be stable for the equivariant dynamics. But the converse is not true. So there may be points on E which are stationary for both my equivariant and augmented flows, but are stable for the equivariant one, but not for the augmented dynamics. There may be directions where the augmented dynamics can escape, where the E is not allowed to, look at. One can solve this by regularizing. So if we put some regularization on the augmented weights, so a penalization term that makes it not go too far away from E, we can actually get equality of these sets. And in particular, if we look at a strong weight decay, we would end up in a situation where the equivariant and augmented flows have the exact same stationary and stable points on E. Okay, now let's see if this also holds in practice. So there are many simplifications here. We have looked at gradient flows and no stochasticity or anything. So let's make an experiment. Let's perform a simple experiment on MNIST. What I do is that I look at 2 CNN architectures as my nominal architectures. And I choose them symmetric with a symmetric and an asymmetric support. And my group action is C4, so the 4 rotations with multiples of 90 degrees. And I let them act on my input space and also on the early layers. Then at some point there is a layer which takes a image feature and turns it into something invariant, and then I keep that trivial action from then on. And then the point is that since my symmetric space is invariant and the asymmetric space is not, we should see we expect that the weights stay in E for the symmetric for the red architecture, and they do not for the blue one. Here one can make a small subtle point. So I have here said that I choose the representations, the rotation representations on all the early layers. One could argue that there might be another representation of the rotation group that makes the blue space invariant. However, one can prove that these do not exist. If one uses the properties of convolutions together with how they act on filters like this, one can actually show that there cannot be any representations for which the asymmetric space is invariant. Okay, so what we now do is that we start our neural networks on E, and then we train them in equivariant mode with the stochastic gradient descent for quite long. So then the hope is that we will find something which is stationary for the equivariant architecture, and then we let the two loose. So close to this hopefully stationary point, we train it in augmented mode and see what happens. And what does happen is exactly what one would expect. So the blue one, which is asymmetric, that goes away from the E space quite fast, and the red one stays close to it. So here on the left we have the distance for 10 epochs. On the right we only have the first epoch. And there we see that actually also under the stochastic setting, we stay close to our result space. And in particular, the red one first goes away and then comes back. We don't really know, so the theory we did before does not really explain this. So this is something that we're working on right now to try to explain and get a bit more precise notion of what is going on. Now, up until now, we have only talked about the dynamics close to E. So if we start equivariant and we have this invariance condition of the architecture, it will stay there. However, if I start somewhere away from E, the theory I presented until now does not say anything. However, there is another set of results about so-called ensembles of neural networks, so kind of what happens in the mean, and there something interesting happens. And this is what I'm going to talk about in the final moments of this presentation. So again, what happens if I start my neural networks away from E? So here I have a situation where I pretend that my group action acts by reflection on the weight space in this green line. Then the green line is the set of equivariant points, those that are fixed by the action on the weight space. And if I'm now starting a neural network away from E, anything can happen. So it might go down to E, but it can also, as we see here, escape E. But if we start a lot of networks like this, and we let the dynamics flow, something very interesting happens. So we see here that we are actually converging in a group sense towards a distribution which is symmetric with respect to reflection in the green line. And this in particular means that if we look at the mean of all these weights, it will always stay on the green line. So in mean, my models will become equivariant. And this is really something interesting. So it seems that augmentation training does not make single networks equivariant, but if we look at an ensemble, it will. So by an ensemble, we mean a number of networks that we train independently, and then we form the model by averaging them. And here the independence does not come from training on different data, but it comes from initializing the networks independently. And I should stress that this equivariance in mean is not an idea of ours. It's not our observations. However, in the existing work, we could find the real results are about idealized limits. So there's one paper about neural tangent kernel limits, so in the end, we make a statement about a linear training. And there's also another work where they talk about Wasserstein gradient flows, and they somehow are also closer to something linear than what we have when we work on a bona fide network. So what we set out to do is to show that we get equivariance also in a ensemble of bona fide finite limit neural networks. And we have managed to do this. And what is interesting is that this invariant condition of L is again important. So if we train an ensemble of networks with a architecture corresponding to an invariant L, and we initialize it in an equivariant way. So if we draw our weights according to a Gaussian distribution, for instance, if we then train it on augmented data, we will have equivariance at all times t, actually. And we can also prove an extension of this to stochastic gradient descent. Then we also need to take the average over the batches that we draw, and also in particular the augmentations that we draw at random in each step. How does one go about proving this? Well, we can actually, what we need to show is that what we showed in the animation 2 slides ago really happens. So I start with my symmetric Gaussian distribution, and then by applying my training flow, it will turn into something equivariant. And the steps are as follows. So first, one proves that under my geometric condition on my architecture, the equivariant, the training flow map I get is actually an equivariant map. Then it's quite easy to show that if I start with something which is invariant symmetric, it will stay symmetric for all t. And then we use the structure of the neural networks to argue that the invariance of the weights is actually enough to show that the network outputs when average turn my ensemble equivariant. This is in some sense a quite interesting theoretical result, in that it gives us a setting where we can actually prove that augmentation leads to equivariance. And it's somehow more realistic than what we did before. No, I think it's quite, it's not initializing my network with weights in a certain subspace. It's not something that one would do in practice, but initializing it randomly using a Gaussian weight distribution is something that one would really do. And we do not, and in that sense, the analysis is non-local. We start it anywhere in space, not on a confined subspace E. On the other hand, there is more work needs to be done to actually make this to really get to the core of this. So for instance, we are always assuming that we have an infinite ensemble here. So we could try to prove some bound on how many ensemble members we need to get this equivariance. And in practice, this really seems to give something, but there are more theoretical work needs to be done. And what is also a bit sad here is that we are again proving some kind of invariance result. We assume that we start our network initialized in an invariant distribution, and then it stays invariant. one would rather want a situation where the equivariance emerges, so that we converge towards the set of invariant weights and invariant ensembles after some time. But this is work in progress. We are coming to the end of the presentation. So let's conclude. I've talked about symmetries in data and symmetries of neural networks today, and there are these two strategies that one could use. One can either augment the data or one could restrict the data. And in particular, there is this canonical way to make a neural network equivariant by confining the weights to lie in the set of linear maps that commute with some representations on the inner layers that I prescribed. And we can both do this for multilinear perceptrons, but we can also include more interesting examples by starting with weights confined to a space L. And the geometry of this space L plays a role. So if it is invariant towards this lifted representation, taking weights to kind of transformed weights, if that is true, a lot of nice things happen for the augmented dynamics. So the space of equivariance weights turns into an invariant set of the dynamics. We get an equality of stationary points between the equivariant flow and the augmented flow on E. And we also get this ensemble result that the ensemble string of augmented data will become equivariant. With that, I thank very much for the attention, and I look forward if there are any questions.
Thanks a lot. Thanks for the great talk. I will stop the recording here and then open it up for questions.